Hello again and welcome back to my 8-bit CPU. So today our CPU is running a very simple program. It's once again it's just counting or calculating Fibonacci numbers, but just for fun I thought we'd count them backwards. So he's starting with the highest two known Fibonacci numbers, so we'll see those in just a moment. I mean, not the highest known, but the highest below 256, which are 233 and 144, and then he's just subtracting the last two numbers known to him, and if all goes well we should end up at 0, which we do, and then he just starts all over again. So this is a very simple program. You can see the assembler instructions for that program here, but we're going to use this program to illustrate the main topic for today, which is our registers and how they interact with each other using the bus. So as I've pointed out a few times before, we have an A register here, and the value of the A register is displayed on this decimal display. We have a B register, and its value is shown here in binary. And down the bottom here we have a C register. Its value is also shown by the LEDs in binary, and the same for this D register. And those are what I call the general purpose registers. And then in addition we have two specialized registers here, which are on the one hand the stack pointer. Now the stack pointer is not being used at all in this simple program, so its value at the moment is 0, and it's going to stay 0 forever. And over here we have the program counter, which contains the address of the currently running instruction. And so this program now is running under the influence of the automated clock, which we had a look at in the last episode. So here it is. Now it's not running at full speed, because at full speed we wouldn't be able to see much. Even now it's a bit fast, but so we can see the Fibonacci numbers counting down, and we can see that the registers are receiving values regularly, and we're going to have a look at in a bit more detail how that works today. So if I just turn the clock to manual mode just for a moment. So at this moment we're going to get to the control logic, which is all of this area down here. But two things I want to point out is that at the moment there are two signals which are on, and that's this signal here, which is register B write, RBW, so that's this LED. And another signal that's on right now is register C enable. That's this signal. And so what that means is that this is the C register over here. And so at the moment that contains a binary value of 5. And the point of the instruction that it's currently running is to get that value of 5 into the B register, which is up here. And so this is one part of the computer, the C register, and this is another part of the computer, and basically they want to exchange data amongst them. So the C register wants to, let's say, broadcast its data, and the B register wants to take that data that comes from the C register. And the way that works is through a bus, and here is my bus. And so the bus is just this, basically it's a collection of 8 wires. It's nothing more than that. And so this C register at the moment is outputting its contents of 5 onto the bus. And in fact you can see it here because I've installed some LEDs so I can see exactly what the values are on this bus. And at this moment it's 5, which is what the C register is putting out onto the bus. And so the B register on the next clock tick is going to take that value and store it inside himself. So if I just advance the clock by 1, there you see, it happened. So now that value which was in the C register has been transferred onto the bus. And then on the rising edge of the clock, the B register has taken that value and stored it inside itself. And that's all that registers do, really. They output their values onto the bus and they read values in from the bus. And so we're going to have a look at how that works. Now, once again, this CPU is heavily inspired by the 8-bit computer that Danita built and documented in a series of YouTube videos. And there are some episodes that he's published which deal in very great detail with the bus, which is just this collection of 8 wires here, and with the way he organizes his registers. So I've put links to those videos in the description, and I would certainly recommend that you have a look at them. And then I'm basically going to extend his work and point out where my design has a few additions or works a little bit differently from his. Now, one of the first differences which you might notice if you look in detail at this bus is that my bus is purely driven by registers or by components which are outputting onto it. So in this case, for example, we see that the program counter is enabling its value onto the bus. So this is the program counter, and at the moment it contains a value of 16. And so that 16 is asserted onto the bus, onto all 8 bits. And so that means that this line really is at 0, so is this one, so is this one, so is this one. This one is at 5 volts, this one is at 0, this one is at 0, and this one is at 0. That's what we call asserting a value onto the bus. And so any other component which would connect to these 8 wires would find those voltages on the lines. And that's the idea of the bus. The bus is just a set of wires which we can connect and disconnect to the various components of the computer using control signals. That's exactly the whole point of a bus. And so we'll have a look in detail at how that works. In this design, for example, our program counter is 8 bits long, and that's a difference from Ben's design, because on Ben's computer his program counter is only 4 bits long. And that means that on Ben's computer, when his program counter is enabling its value onto the bus, it's actually only enabling 4 bits, and his 4 higher bits are not set at all. They're not 0 and they're not 1. They're not connected to anything. And of course, that's not a good idea, because some other unsuspecting register might be trying to input a value from the bus, and so it would get 4 definite bits and 4 what we call floating bits. They wouldn't be connected to anything. And so what Ben did to remedy this situation is he has some pull-up resistors which is connected to every one of his 8 bus lines. And those pull-down resistors he has, actually, they sort of force any line which is not being asserted to be 0 volts through that resistor. I haven't done that because on my CPU there isn't any situation where a component would only be enabling a certain number of bits. Every single component on this computer, all of the registers, the ALU, the program counter, this instruction register doesn't output, but RAM can output. They all assert all 8 bits at once. So I don't need any, let's say, default value on the bus, because I'm always asserting all 8 bits. And so that's the first difference. If you look here on this bus, you won't find any pull-down resistors, because I don't need them. And to have a look at some of the other differences, I'm going to change the camera so we can zoom in a little bit on the details of some of these registers. All right, so here we have a close-up view of the D register and the C register, and we can actually also see the stack pointer, which is just a register as well, just like C and D. The program counter here works a little bit differently, and we'll talk about that in a future episode. But so let's have a look at the D register here. And in fact, the LEDs are hooked up down the bottom here, but the actual register circuitry is basically these 2 integrated circuits up here. And so we have, first of all, we have these blue wires which are connected to the 8 bus lines. So in fact, on the top of this chip here, which is a 74HCT245, and it performs exactly the same function as the 74LS245 in Ben's computer, these are all connected to the inputs of that chip. But not only that, they're also connected using these 8 wires to 4 pins on the top and 4 pins on the bottom of this chip, which is a 74HCT377. And let's first have a look at that chip. So here is the datasheet for that chip. So it's the we're using the 74HCT377. And so that's a D-type flip-flop, which has an enable signal. And the big advantage is that it's 8 bits large. If you remember from Ben's video, he actually needs 2 chips for each register, because he's using an HCT173, and that is a D-type flip-flop which can only store 4 bits. And so this 377 is a little bit bigger, and it can actually store 8 bits, which is what we want for a single register. So if we have a look at the pinout here, So we have an enable signal, and the enable in this case means write. So it's a write enable signal. And we have a series of D lines here, which are the input wires. And that's these blue wires which are coming in straight from the bus. And so they're connected to all of the D pins on the 377. And then if the enable signal, which is actually this yellow wire down here, this one, which runs up to the control logic, if that's enabled, then those values, whatever values are coming in from the bus on these blue wires, they'll get set into the 8 single-bit latches inside of that chip. And when that happens, that's the whole point, if we have another look at the pinout here, then the Q lines will show the value that's currently stored. So at some point, if we enable it, well then those Q lines will change to reflect whatever's on the bus. But if we're not enabled, then nothing happens. So for example, in this case, you can't see it right now, but there's some totally different value on the bus. And even though I advance the clock, nothing's happening with the D register until that enable line gets enabled. And of course, that's not the case right now. So this value is just going to stay there until we actually instruct the D register to take in a new value from these blue wires. And as long as it's not doing that, it's going to keep whatever value is stored in there. And so those values are output on the various Q pins, and that's these green wires. And so the way we can actually tell the D register to output its value to other components on the bus is through this first chip here, through the buffer. So these green wires are all connected to the 8 pins on the bottom of this chip. And let's have a look at its datasheet. So we're using the HCT245, 74 HCT245, which is just the CMOS version of the 74LS245, which is exactly the same chip that Ben uses. And all it does is it's what's called Tristate logic. So it's going to connect whatever is on the inputs here. So in our case, those would be these green wires on the inputs over here. And if we enable it, there's an output enable signal. So if we enable that chip, then it's going to connect those signals onto the blue wires, which is the bus. So that is a signal which comes into this chip, which is over here, and that's our enable signal. So that's the D enable signal, and that's the D write signal. So that's how that works. We get values coming in from the bus. If we're instructed to do so, they get written inside this register, and that they get output immediately onto these green wires. And if at some later point we get an enable D signal, well then those green wires are going to pass through this buffer here, this Tristate logic, back onto the bus. And that's all the register is, really. So we're using the same buffer chip, but we're using this HCT377 so that we only need one chip to store all 8 bits. And now the fact that we're using that chip has a few implications. If you have a look at the pinout again in detail, so we have a write enable signal. That's good because we want to control when we write and when we don't write to the chip. And of course we have a clock pulse. So even if I were to assert this write enable signal, so in this case it's an active low, which means assertion means I'll pull it low. Even if we were to do that, the actual write won't happen until a rising clock edge. So we're still clocking in values, which is good. But you'll notice that this chip doesn't have an output enable. So its Q output signals are always enabled, no matter what's happening. And that's actually good, because if you look back at Ben's videos, he uses the 74LS173, which has an output enable signal, and he needs to activate that permanently, because we want to see the value that's in the register and show it on here, even if we're not outputting on the bus. So right now, the bus contains some totally different value because it's not being enabled at all by the D register. But the D register still has a value, and we would still like to see what it is. So at the moment, all these LEDs are hooked up to these green wires, which are the outputs from that register chip. And so it's actually a good thing that we're always enabled. So we're not going to miss that output enable signal at all. But another signal that this chip doesn't have is a reset. And in one of the later episodes in Ben's series, you'll see that he connects up a single switch to all of the reset signals and all of the various components of his computer. And I have something similar, which we'll get to, but of course my reset signal can't reset this register because it doesn't have a reset function. Now, you might think, okay, that's going to be a problem. How can I ever reset my computer? But if you think about it, it's not such a huge problem, because when you run a program, for example, the program that we're running today, which is this one, well, all you really need to do is to write code to put the right values, the values that you're expecting, in the registers when the program starts. So if I can simply make sure that we start at address 0, i.e. that the program counter is 0, well, that ought to be enough, as long as I make sure in my program that I don't suppose anything about the registers and that I initialize them properly. And in fact, real-life CPUs work exactly that way. When you turn the power on a CPU, you have no idea what values will be in the registers. They're not reset at all. And so by programming it correctly, we're actually not going to miss the reset signal either on this chip, on this 377. So because of those reasons, I've just gone ahead and used that instead of the 173. That saves us a chip. And more importantly, it actually allows me to put 2 registers on a single breadboard. And so we've just had a look at the D register, but if you have a look at the C register, that works in exactly the same way. So that too has a 74HCT245, which enables whatever is being output by the register, which is a 74HCT377 for the C register. So in this case, it's a 5 that's being output on all of these green wires. And so that will be output onto the blue wires, which are the bus wires. And so they're connected to these blue wires, which are connected to those blue wires, so this is all basically just an extension of the bus, which is running all the way to here across these 2 registers. And so at several stages on the way, we're basically connecting to the bus. So we're connecting this buffer so we can output a value from the D register. We're connecting the actual register so we can input into the D register. We're connecting that buffer so we can output the C register. And then we're connecting finally the actual C register so we can input from the bus into the C register. And so by using 1 chip instead of 2, we're saving a bit of space. And okay, the wiring gets a bit tighter, but it's perfectly possible to connect 2 registers on a single breadboard. And well, one of the reasons I did that is because I decided pretty early on that we're going to need more than Ben's 2 registers. And in fact, we have 6 program addressable registers. We have the stack pointer up here, which works in exactly the same way. So it too is connected to the bus along these blue wires. So on the way, the program counter is obviously interested in what's on the bus as well, but we'll ignore that for now. And so we get to the stack pointer here, and so that too has a buffer. But of course, this buffer is working in the opposite direction. So it's going to connect or not connect its top pins to its bottom pins, whereas these buffers are connected to connect or not, depending on the enable signal, the bottom pins to the top pins. And if you remember, if you have a good look at the HCT245, you'll notice that it also has a direction pin. So we can choose whether we're actually connecting the A registers, considering them to be inputs, to the B registers as outputs, or if we're working the other way around. And so all that we need to do there is, in the stack pointer, that direction signal is connected to a different value. So here on the stack register, it's actually connected to 0 volts, to ground. And on the C register, it's connected to 5 volts, as it is on the D register. And so in this case, it's high, which means that the signal is going that way. And in this case, it's low, which means that the signal is going that way. And the only reason for that is geometry, because I wanted to put the LEDs on the stack pointer on the top here. And because actually, when building the program counter, it turns out that the bus it's more practical to have the bus on the bottom side. So, well, I just built my stack pointer in exactly the same way. But apart from that, this register is exactly the same as that one. It's also an HCT377, and it inputs from the bus, stores the value, puts the value out on the LEDs, and puts it out onto these green wires. And so that's how our registers work. So just for completeness, here is a schematic of the register, the way we've built them. So at the bottom here, we have the D0 up to D7. That's basically the bus. And so that's connected to any other data consuming and producing parts of the computer. And so that bus is connected on the one hand to the input pins of the 74, in my case HCT 377, which is our register chip. And so those inputs, they'll get stored into the register if this enable signal, which is an input control signal, it's the write signal for our register, if that's asserted, and at that time it'll arrive on the next rising clock edge. So when that happens, whatever is on the bus at that time will get latched into the register. And it will be output immediately onto these Q lines, onto the green wires in my circuit. And that's because this chip doesn't have an output enabled. The output is always enabled, so and that's what we want. And so we have these LEDs, which we've connected up here. And we also connect these outputs back to this 74 HCT 245 buffer chip, which uses Tristate logic to either connect this signal or not back onto the bus. And whether or not it should connect is controlled by this signal, which it calls the enable signal. And so that's connected to the enable of our register. So that could be the B enable, or register B enable, or register C enable, or register D enable, and this would be register B write, or A write, or C write, or D write, or whatever. And so it's really quite simple. We have one chip which we use to store the values coming in from the bus and to keep them, and another one to output whatever value is being kept back onto the bus. Now, one little detail that I want to go into is these LEDs. So if you have a look, they're connected directly to these Q outputs. So this anode of the LEDs will be either at 5 volts or at 0 volts, depending on the value of the bit that we're looking at. And so the cathode is not connected directly to ground. It's connected through this resistor. And that also is a slight difference compared to Ben's computer, because Ben is using the 74LS series of chips. They actually have some pull-down resistors built into them. And for whatever reason, in Ben's case, those pull-down resistors, they work fine and they limit the current in a way which is sufficient for his design. However, I noticed that with my HCT series, I was drawing, when I connected an LED directly to ground, so without this resistor, I was drawing an awful lot of current. I was drawing between 40 and 50 milliamps for each LED. So if I had 8 LEDs, all drawing 50 milliamps, that would be 400 milliamps just for one register. And remember, I have 6, and I have an ALU, and I have control signals, and I have RAM. And so for a single register to draw almost half an amp meant I was looking at a computer that was going to draw 4 or 5 amps. And in addition, sending 50 milliamps through an LED permanently didn't seem like a very good idea. So in contrast to the LS series of chips, the one disadvantage of using the HCT series of chips is that I need current limiting resistors for my LEDs. And so one way would have been to add a resistor to each LED, and then I could have controlled the current precisely for each LED, but I haven't done that because, as we'll see on the physical layout, that's a little bit cumbersome to do. So I've used a single resistor, current limiting resistor, which all the LEDs on the register share. And that has one interesting side effect. Because I have a single current limiting resistor, I'm basically determining what the current will be through that resistor. So if I say that these LEDs, if these are the red LEDs, well, they're going to drop, if they're on, they're going to drop about 1.8 volts. And up here, we're going to have, let's say, 5. So on this side, I'm basically going to have 3.2 volts. And so I'm limiting the current through this resistor from 3.2 volts to ground. So if I'm using a 100 ohm resistor, for example, I think I'm using 150 ohms. So let's say it's 150 ohms, and let's say that this is 3 volts. Well, in that case, I'm limiting the current, the total current, to 20 milliamps. And so if only one LED is on, well, then 20 milliamps will flow through that one LED. But if two of them are on, then we'll still have 20 milliamps through this single resistor, but we'll have 10 milliamps through each LED. And so they actually become less bright. And if I have 3 LEDs on, well, I'll be sharing my 20 milliamps amongst 3 LEDs. So I'll have 7 milliamps in each of them. And so depending on the value which is being shown, if I have more or less LEDs which are showing a 1 state, they will actually change in brightness. And that's a little bit of an odd effect when you look at it the first time. And if I were to rebuild this computer in some future, I would probably use LEDs with built-in resistors, and because then I would have a current limiting resistor for each LED individually, and so I wouldn't be sharing a single fixed current value amongst all LEDs. But for the moment it works once you know and are aware of the fact that the LEDs can change brightness, but it doesn't change anything in the meaning. It's simply a consequence of the fact that they're all sharing a single current limiting resistor. Well, you know, computer works fine anyway. And so here you can actually see what I was talking about. So this C register is basically counting down the Fibonacci numbers. So it has high values with lots of bits set, and it counts them down, and it gets to low values with very few bits set, and eventually it gets to 0. So if you have a look at this D register, you can actually see that the brightness of these LEDs is pulsating. So at some points it's less bright, and at some points it's more bright. And the reason for that is that all of these 16 LEDs are all sharing the same current limiting resistor, which in fact, I don't think you can see that on the video, but it's over here. It's a 100 ohm resistor. And so the cathodes of all of these LEDs are connected to this rail, to this minus rail over here. So on my board, that rail isn't ground. That rail is probably at around 3 volts. It's simply a convenient way to connect all of the cathodes of all of these LEDs together, because that is a single rail, that's a single electrical connection. And so that's connected to ground through this resistor. And as I explained before, one of the side effects of organizing things that way is that these LEDs actually vary in brightness depending on how many of them are lit at the same time. But using that technique, we've certainly reduced the current from, let's say, 50 milliamps per LED down to, in this case, a maximum of 20 or 30 milliamps for 2 complete registers for 16 LEDs. And that's certainly a big advantage. And as you can see, even if the brightness is varying, it's still perfectly possible to tell whether it's lit or not. And so for the operation of the computer, it really doesn't have any consequence. So that more or less wraps up our episode for today. So we've had a look at our 4 registers, the A register and the B register. So now we know that the registers are actually, each register is implemented by 2 chips. There's an actual register chip, which stores the values, and then there's a buffer chip, which enables the contents out onto the bus. And so we have that for the A register, for the B register, for the C register, for the D register, and also for the stack pointer. The one slight difference with the A register is that we haven't hooked up any LEDs here to show the value in binary, but instead we've hooked up this decimal display, which we'll dedicate a separate episode to seeing how that works. Now, what I intend to do in the next episode is have a closer look at our memory, at our RAM, random access memory. And so that's located over here. This is the actual RAM chip. And as I explained in the introduction, we're using, let's say, a Harvard-inspired architecture where we're using 2 RAMs, or we're splitting our RAM in 2. So we have a part which we use for data and for the stack, and we have a separate part which we're using to contain the program. And so we're switching between these 2 RAM halves, if you like, using a signal here, which we're calling program memory. And so we'll have a look at how that works in detail. Apart from that, we have a memory address register, which is this one. And we also have dip switches, which are these, which we can use by switching the memory into programming mode. We can actually enter this program into program memory. So, I hope you enjoyed this episode, and we'll see each other in the next one.